at synchronizing power and torque. This comes into play when there is a disturbance on the alternator, and the synchronizing torque tends to pull the rotor back to its original position, and the synchronizing power is equal to pi over 180 times EV over XS cos delta. This is watt per electrical degree. If we want to change it to mechanical, that becomes P pi over 180 EV over XS cos delta watts per mechanical degree, where P is your number of pole pairs. The synchronizing torque is equal to the synchronizing power divided by omega S, where omega S is your synchronous speed in radians per second. If the armature resistance is not neglected, PS is equal to EV over ZS cos beta plus delta times d delta, where beta is the internal impedance angle. In the generating mode, electromagnetic power developed in watts per phase in electrical radian of rotor displacement P, EMG, is equal to E over Z cos beta minus V over Z cos beta plus delta. Sorry. Then if we differentiate it with respect to delta, we have EV over ZS sine beta plus delta. To convert it to mechanical degrees, that will be delta EV over ZS sine beta plus delta, where delta is equal to P pi over 180. Now let's look at an example. A 3,3 kilovolt 3 MVA 6-pole alternator has a reactance of 0.25 per unit. Calculate the synchronizing power and the corresponding torque. So we need to calculate P synchronize and the synchronizing torque. Now the first step, E is equal to V plus IA ZS. So therefore that will be 1 angle 0 plus 1 angle minus 36,87. The power factor in this case was 0,8 lagging. Times 0,25 at an angle of 90 degrees, which gives us 1.167 at an angle of 9.9 degrees. The synchronizing power is equal to delta VE over XS sine 90 plus delta, which gives us 3 pi over 180 times 1 times 1.167 divided by 0,25 sine of 90 plus 9,9 degrees, which gives us 0,241 per unit. To convert back to actual power, P synchronizing is P synchronizing per unit times S, which gives us 0,241 times 0.3, which is equal to 723 kilowatts. The synchronizing torque will be the synchronizing power divided by omega, which is 0,241 divided by 2 pi and 16,667, which gives us 0,0023 per unit. And again, to convert back to actual power torque, that will be 0,0023 times 3 MVA, which is 6,904 Newton meters. If we have a look at another example, which is a 1.5 MVA, 6,6 kilovolt, 4-pole star connected alternator, has a synchronous impedance of 0,5 plus J 5,5. Operating at full load, power factor of 0,8 lagging. Let's calculate the synchronous impedance. Electromagnetic power developed, and the synchronizing torque. First step is to calculate the full load current, that is S divided by square root 3 V line, which is 1500 divided by square root 3 divided by 6,6, gives us a current of 131.22 amps. The base impedance is V over I, all per phase, which is 3810,5 divided by the current, which is 131.22. It gives us an impedance of 29,04 ohms. To convert to per unit, that will be the actual divided by the base. So that will be 0,5 plus J 5,5 divided by 29,04, which gives us a value of 0,19 at an angle of 84.81. Next step is to calculate the induced EMF. E is V plus IAZS, which gives us 381.0,5. Always work per phase whenever we work with three-phase work, and therefore the current is 131.22 at an angle of minus 36,87 times 0,5 plus J 5,5, which gives us a value of 4,329.57 at an angle of 7,14 degrees. The developed power, PD, is equal to E over Z times E cos beta minus V cos beta plus delta. So that gives us 4329.57 divided by 5,523 times 4329.57 cos of 84.81 minus 3810.5 cos of 84.81 plus 7,14, which gives us 408.668 kilowatts per phase, and total will be 3 times that, which is 1225.98 kilowatts. Synchronizing power which is delta EV over Z sine beta plus delta, which is 2 pi divided by 180 times 4329.57 times 381.0,5 divided by 5,523 sine of 84.81 plus 7,14, which gives us a value of 104.21 kilowatts per phase. To convert to torque, we take the synchronizing power divided by omega, which is 104.21 times 60 divided by 2 pi 1500 revs per minute, gives us a value of 1990.26